Hello guys, hope you are doing well. In a new session, I will be talking about the second section of chapter 5, which is about the reaction rate. At the beginning, we will be talking about the factors influencing the reaction rate, and then at the end of the section, we'll be determining the rate law and we'll be solving different types of questions. And then at the end of the session, we will be solving the standardized test prep with the 35 questions to review the chapter 5. Guys, we have a field in chemistry that relates the reaction mechanism and the reaction rate. That field we call as the chemical kinetics. So here we have got a definition of chemical kinetics that refers to what? To the any field of chemistry related to the reaction rate and the reaction mechanism we call as the chemical kinetics. That's for the term of definition. You have to know what's a chemical kinetics. But the main topic is a reaction rate. What's a reaction rate? The reaction rate is the change in concentration of reactant per unit time as a reaction proceeds. Change of concentration of reactant per unit time. So in this section, we will be just talking about the reactant side. We will not talk about the product side. Why? Because those chemicals that they determine the speed of the reaction, or they will be considered as those species that effect on the rate of the reaction, are the reactants. The product, they do not affect on the rate of the reaction. And the unit, guys, can be determined as molarity per second or molarity per minute. So in both are useful, but the one molarity per second is much useful. Let me just provide an example to understand the rate or reaction rate, guys. If a process converts 2 molarity of reactant per second, or a process converts 8 molarity per second, which one should be logically a faster mechanism? Of course, the one that consumed or converted a higher concentration, a higher amount of the reactant to the per specific period of time, which is a second or a minute. So this is a slow mechanism compared to the 8 molarity per second, which is a faster mechanism. A slower mechanism, this is a faster mechanism if we compare those two with each other. What are the factors that influence on the rate of the reaction? The factors that influence on the rate of the reaction, guys, any factor that changes the collision frequency or effects on the collision frequency and collision efficiency, that can be one of the factors considered to be one of the factors that influence the rate of the reaction. Collision frequency and collision efficiency, that are the factors that influence the rate of the reaction. How many factors change the collision efficiency and collision frequency of the reactions? We have got 5 factors: the nature of reactant, surface area, temperature, concentration, and presence of catalyst. We'll be talking about them in detail. Okay, guys. Let us talk about the nature of the reactant first. Nature of reactant. Have a look, guys. We have got an example that the hydrogen reacts with chlorine and hydrogen the same reacts with nitrogen. When the hydrogen reacts with chlorine, the mechanism reacts much faster or vigorously, and the mechanism is a very fast mechanism. But when the same hydrogen reacts with nitrogen, there will be a slow tendency to react. What's the reason behind this? Here we have got the bonds between chlorine is a single bond, but the bonds between nitrogen we have got triple bond. So which one is much easier to break down? The single bond is much easier to break down, can be easily broken, but the triple bond too difficult to break. That's why it slows down the mechanism of the reaction. But this refers to what? Refers to the nature of those chemicals. Those chemicals in nature, they are like that. Another example, guys. We have got oxygen and oxygen. Oxygen reacts slowly with iron. Rusting of iron is a slow mechanism. It needed several days. But oxygen reacts with the group 1 elements like sodium vigorously and a more rapidly mechanism. This refers to what? The reason is what? Is the nature of those chemicals. Oxygen has a high tendency to react with sodium, but a low tendency to react with iron. This is the first factor that refers to the nature of the chemicals, the reactants. The second, guys, is the surface area. The surface area. Guys, this surface area, the gaseous mixture and dissolved particles can mix and collide freely. Therefore, reactions involving them can occur rapidly. Those reactions, they contain gases and dissolved in aqueous medium. They move much freely than the solid state. That's why most of those reactions are much rapid than the reactions contain solid state. But we cannot increase the surface area of gases and aqueous, or we can say liquid as well. In heterogeneous reactions, which we mean the reactants they exist in different phases, the reaction will depend on the surface area of contact of the reaction to the substances. And guys, the surface area, we can conclude that it's only for the solids, for the solid substances. Why? Because the only physical state of matter we can increase or decrease the surface area is solid state. The other status, we are not able to increase the surface area. Let us take an example and determine how the surface area works. Here we have got a carbon, lump of carbon. A lump of carbon means a lump of carbon. This is a lump of carbon. Okay. With the powdered carbon. This lump, smash it to be powdered carbon. Which one has a greater surface area of contact with the oxygen? Of course, as we smash the lump of the carbon, there will be a higher surface area to be in contact with the oxygen. That's why a higher surface area for the oxygen lets the collision frequency to be more and the collision efficiency as well. As the collision efficiency becomes more, there will be the rate of the formation of CO2 becomes a faster and here slower compared to the second. So a lump of carbon burns much slower than the powdered one because the powdered one has a much higher surface area. The reaction rate is directly proportional to the surface area. So as we increase the surface area, that increases the reaction rate as well. The heterogeneous reactions, guys, we talked about the homogeneous previously. The heterogeneous reaction means the reactant are in two different phases. So here we have got zinc reacts with hydrochloric acid. Zinc is solid and hydrochloric acid is aqueous. So this reaction is a heterogeneous reaction because the phases of chemicals in the reactants, they are different with each other. And as a reminder, homogeneous reaction, those reactants and products exist in a single phase, which we talked about it previously. And the surface area work is only for the heterogeneous reactions, means there should be solid in the reactant, and increasing the surface area increases the reaction rate, makes the rate of the reaction much faster. The temperature, guys, the third factor influencing the rate of the reaction, guys, as the temperature increases, that increases the kinetic energy of molecules. Increasing the kinetic energy of the molecules increases the motion of the particles, or we can say the movement of particles in the system. And as the movement of particles in the system increase, what will happen to the collision frequency and collision efficiency? Collision increases between the particles. As collision increases with the particles, rate of the reaction, which represents by R, increases. So guys, the effect of temperature with the rate of the reaction can be stated as they are directly proportional to each other. As temperature increases the kinetic energy of the system, and then increase the movement of particle, and then increase the collision, and then the rate of the reaction will be increased through increasing temperature, guys. At a higher temperature, more particle possess enough energy to form the activated complex when collisions occur. That means increases the collision. A rise in temperature produces an increase in collision energy as well as in collision frequency. So beginning from, this is given in our book, beginning from room temperature, increasing 10 degrees of Kelvin or 10 degrees of Celsius increases or doubles the rate of the reaction. Means what? Means if the 1 molarity per second at 25 Celsius, it will be 2 molarity per second at 35 Celsius. Increasing 10 degrees Celsius, this is usually not for all the reactions, doubles the rate of the reaction. That's the representation of the relation of temperature with what? With the rate of the reaction. The fourth one, guys, which is concentration. The concentration, simply I can present the concentration here in these models, which is presented in our book. We have got the 4 different systems or 4 different reactions, collisions, guys. In the first one, 2 substances or 2 atoms, there will be 1 possible collision. Why? Because this can collide only one other atom. But if we increase the number of atoms to 4, there will be 4 possible collisions. Why? Because one of the atoms collides both the atoms and the other atoms, so there will be the 4 collisions between those particles. If we increase into 5 atoms, there will be the number of collisions 6. This 3, the other one 3. But if we increase to 8, there will be 16 possible collisions. Guys, as the concentration of the chemicals increase, what happens to the collision frequency or collision efficiency as well? The frequency of the efficiency becomes much frequent, the collision becomes much frequent, and then, so we can say that as the concentration of reactant, let me write it. as concentration of reactant increase, that increase what? The collision frequency, and then increase in collision frequency increases the rate of the reaction. So what's the relation between the reaction rate and concentration? Is directly proportional, which is increasing the concentration of particles in a system increases the collision frequency and efficiency as well. That increases the rate of the reaction or the reaction rate. Another example, which is given in this figure, guys, said we have got two combustion of carbon. A, carbon combusted in pure oxygen, which is 100% oxygen. B, carbon combusted in oxygen of air, which is 20%. You know that the oxygen in air its composition is 20%. So which one burns much faster? Of course, the one with the pure oxygen. Why? Because with the pure oxygen there is no any impurities, and the oxygen frequency, the frequency of the collision and efficiency as well increases. But here we have some other impurities like nitrogen and the other trace, the elements, the other gases in air. So the 80% is not oxygen of the air. That's why the difference can be observed from the figures. The oxygen in pure air is much sparked, much lighter than the oxygen in the air that the carbon combusted in air. So this is represent what the difference of concentration. Here, a high concentration let us to be have a faster mechanism of combustion of carbon, but a lower concentration of oxygen, a lower or a slower mechanism for combustion. In this, the combustion of oxygen is 5 times faster than the oxygen in air. Why? Because the concentration is 5 times as the concentration of oxygen in air. The last factor, which is about the catalyst. Guys, previously you have studied the catalyst. Catalyst is a chemical that speed up the reaction, but itself is not a part of the reaction or is not participating in the reaction as the reactant. A catalyst is what? Is a substance that changes the rate of a chemical reaction without itself being permanently consumed. So the working mechanism of catalyst is what? It increases the reaction rate, but itself is not used or consumed permanently in the reaction, or is not a part of the reaction. The processes that we use catalysts, where they call it the catalyzers. So any reaction that we use catalyst, we call the reaction is catalyzers, means catalysts have been used in the reaction. Adding of a catalyst increases the rate of reaction because it provides alternative activated complex that require a lower activation energy, so number of effective collision increases and also reaction rate increases. So presence of catalyst increase the reaction rate through increasing the collision frequency, and there will be an effective collision between the particles. That's why there will be an increase in the rate of the reaction. We'll be talking about the effect of catalyst, that what happens to the IC, EA and E prime in the coming page. In terms of homo and hetero, we have got two types of catalysts, guys. A homogeneous catalyst, and a heterogeneous catalyst. A homogeneous catalyst will be providing examples. Is a catalyst which has the same phase as the reactants in the reaction. So if the phase of the catalyst is the same as the reactant in the reaction, but a heterogeneous catalyst has a different phase than the reactant in the reaction. Which one is more effective? Graphically, we will show that the heterogeneous catalyst is more effective. We mean increases the rate of reaction much faster than the homogeneous catalyst. Presence of heterogeneous catalyst lowers activation energy more than the presence of homogeneous catalyst. This statement tells us that the heterogeneous catalyst is much effective. Activation energy affected EA mean only by the catalyst when the catalyst affects or presents reduces the activation energy, and we'll be talking about it graphically in the coming page. Guys, here we have got an example, a figure which represents the catalyst. When we have a decomposition of H2O2, which is hydrogen peroxide, for the decomposition of H2O2, we added MnO2, which is manganese dioxide. It's a catalyst, works as a catalyst. This MnO2 provides a better path of reaction, a shorter path of reaction to the H2O2, to the decomposition of H2O2. So there will be a faster rate of mechanism, and the H2O2 rapidly decomposes into oxygen and H2O. Both the oxygen and water appears as gases because the energy released by the reaction causes much of the water to vaporize. In this figure, we use the MnO2 to decompose H2O2 much faster by using MnO2, which is a catalyst, use it to decompose the reaction much faster. Okay guys, graphically we will show what's the effect of heterogeneous and homogeneous and what the catalyst increases or what the catalyst decreases. Here on this graph we have got four paths of reaction, four paths. The first one, second, third, and fourth. The first one is uncatalyzed. Uncatalyzed means the cat is not catalyzed, we didn't use catalyst in the process. The second one and the third one, we use it for the second chemical catalyst and the third enzyme catalyst. This process we call as a homogeneous process. Why? Because the enzyme and chemicals, we have examples I'll be showing. They have the same phase as the reactants in the reaction. That's why they are homogeneous reaction or homogeneous catalyst. The last one, the fourth one, is a heterogeneous process or heterogeneous catalyst like MnO2, manganese dioxide. Guys, the effect, you can see uncatalyzed has a higher activation energy than the catalyzed. So what a catalyst, here I have written, so it's not a catalyst, reduces EA prime unactivated complex, but not enthalpy change. So what happens to the EA as we add the catalyst into the system, or EA prime as well, and AC, what happens? Reduces. So catalyst reduce three quantities: EA prime, and activated complex, but does not change the delta E or delta H of the reaction, guys. Because the delta S, when it reduces the EA, it reduces the EA prime by the same factor. That's why we will get the same change of energy. And the position of reactant and product is constant. We do not have different positions to have different energy of the reactant and product to get a new enthalpy change. We do not have change in enthalpy here. A heterogeneous catalyst is much effective than the homogeneous. How? Guys, you can see a heterogeneous one is much shorter than the homogeneous process. And a heterogeneous catalyst can be regenerated much easier than the homogeneous. Guys, the heterogeneous, we have got two process, absorption and adsorption. The absorption, an example for the absorption, when we pour a droplets of water on tissue, the tissue is going to absorb all the water and chemically react with water. But adsorption, reaction on the surface, like when we pour droplets of water on a paper, the paper is not going to absorb it. It's just going to react on the surface with water. That's the example of the adsorption. And the absorption is for the homogeneous, guys, which chemically reacts with the reactant. But the adsorption for this is for homo, this is for hetero. So the hetero is chemically, homo chemically reacts with the reactant, which the absorption, but the hetero just reacts on the surface. That's why we call the adsorption for it. And which one is much easier to be regenerated? Of course, the one that reacts on the surface. That's why we said the statement, the adsorption, the heterogeneous is much easier to be regenerated. Why? Because catalysts, they both regenerated. Guys, example for the homogeneous catalyst, here we have got I. I negative is a homogeneous catalyst. Why it's homogeneous catalyst? Because its phase is aqueous and the H2O2 is aqueous. So in this process, it has the same phase as the reactant. That's why it becomes a homogeneous catalyst. But have a look on the other reaction, guys. If for H2O2, which is liquid, okay, when we use MnO2, which is solid, the MnO2 is solid, which catalyst, and H2O2 is liquid, they have different phases. The catalyst has different phase with the reactant. That's why it becomes a what? A heterogeneous catalyst. A heterogeneous catalyst. We will be talking about the difference between catalyst and intermediate. They both appear in the mechanism, in the steps, but they disappear in the main equation. So let us talk about the differences between them, guys. Have a look here. We have got two steps on the net equation. A catalyst, guys, catalyst appear in the reactant of first step and product of the last to be regenerated. Reactant of first, product of last. But intermediate, product of a reaction and reactant of Camin reactions or Camin steps. It appears in a product of one step and reaction of the following steps, or product of the first and reaction of second, if there are two steps. Guys, have a look. A and A cancel it out. So A appears in the phase in the reactant and the product of the last, and then A it becomes a catalyst. C in the product of the phase and then reactant of the following, it becomes an intermediate. That's the difference between catalyst and intermediate. You have to know the difference between them. Metals are used as heterogeneous catalysts because they increase the concentration of reactants. So the heterogeneous catalysts, usually they work as increasing the concentration of the contact between the reactants, and so by what? By adsorption process, which we talks about the adsorption process, and collecting atoms, ions or molecules and binding to make bonds on metal surface. The atoms, they bind on the metal surface much faster, and that increases the rate of the reaction. So metal catalysts, they are heterogeneous, also increase the concentration of reactant. They act as increasing the concentration of the reactant. The effect is the same as increasing the concentration of the reactant. That's probably about all about the influencing factors, which we talked about. We will be talking about the rate law, how to find the rate law and the possible mechanisms of solving the questions, guys. But at the beginning, by providing an example, I will be showing you what's the rate law and how the chemicals they act on the rate of the reactions, guys. Here for this reaction, we have got two reactants, nitrogen monoxide and hydrogen, guys. For all of the reactions, most of the processes, the chemicals in the reactants, when we have more than one reactant, they do not have equal effects on the rate of the reactions. They have different effects on the rate of the reactions. They are differently changing the rate of the reactions. In order to know the effect of individual reactants, we have to change the concentration of that reactant and let the other reactants to be constant. Because whenever I do something with a group, in order to know the effect of me in the group, I have to walk and then the rest in the group stop walking. So there will be the effect of me. The effect of me will be appear. But this is an example for the rate law as well. There are several reactants. In order to know the effect of individual reactants, we have to change the concentration of that reactant and then let the other reactants stay constant, their concentration stay constant. Guys, the reaction rate is the relationship between the concentration of the reactants and with the rate of the reaction. In order to know the effect of individual reactants, we have to change the concentration of that reactant and then let the others constant. We will be processing. So in this part, we will just discuss about the effect of changing concentration on the rate of the reaction. The rate law depends on or represents what? The relationship between the rate of the reaction and the concentration of reactant. Guys, experimentally, the scientists, they have done two experiments. Why? Because we have got two reactants. First, according to the first experiment, they let the initial concentration of nitrogen monoxide constant. So in the first, NO is constant and changes the concentration of S2. Changes. They change it how? When they double the concentration of S2, doubles the rate. And when tripling the concentration of H2 triples the rate. So if we can write the rate as R, this is the rate of the reaction, is directly proportional to the what? To the concentration of hydrogen to the power of 1. Why? Because doubling this 2 to the power of 1 doubles the other. Tripling this 3 to the power of 1 triples the other. Quadruples this 4 to the power of 1 quadruples the rate. That's the effect of H2 on the rate. Let us discuss the effect of the NO by what? By having the same initial concentration of H2 and the concentration of nitrogen monoxide is varied. We change the concentration of nitrogen monoxide. When NO doublet, the rate changes by fourfold, increases to fourfold. When it's doublet, triplet, the rate changes to ninefold. So how to represent this? Doubling this lets the rate to be quadruples. So 2 must be to the power of 2. The order, we will be talking about the order, is 2 here. So 2 to the power of 2 will be 4. 3 square, 9-fold. 4 square, 16-fold, and so on. How to write the rate law for the reaction? This is the rate law. The rate law always is in this form. K, which is the specific rate, we will be talking the specific rate constant, the concentration of reactant to the power of orders. We'll be talking about what are the order, what's K, and how to find them. So in order to write the rate law for a reaction, we represent R, which is the reaction rate, equals to specific rate constant, reactant concentration to the power of order. Here the order of hydrogen is 1. Why? Because it's directly proportional to the rate of the reaction, but the order of the nitrogen monoxide is 2. Why? Because its effect is twice as the hydrogen, and it quadruples, or if we change, or if we double this, quadruples the rate. If we triple this, ninefold the rate. That's why it has an order of 2. So as you can see, the hydrogen and nitrogen monoxide, they have different effects on the rate of the reaction. As I told you, the chemicals in the reactant, they differently changes the rate of, or affects the rate of the reaction. How to write the rate law for the reaction, guys? An equation that relates the reaction rate and concentration of reactant, call it a rate law of the reaction. The rate law represents what? The relationship between the reactant concentration and the rate of reaction. Let us use this equation, guys. This is a hypothetical equation. N with the coefficient of A, M the coefficient of B, to form a product. Here we do not consider the product into calculations. Why? Because those chemicals which are in reactant, they only affects on the rate. How to write the rate law? Usually the rate law or reaction rate equals to K, concentration of the reactant, to the order of the reaction. K is a specific rate constant, and these are the molar concentration of A and B. N means the order of A, M means the order of B. We'll be talking, let us talk about the order of the reaction, guys. The power to which a reactant concentration is raised is called the order of the reaction. So what's the order of the reaction? The power of the concentrations is the order of the reactions. Let me provide some information on the order, guys. Order N and M, they are small integers. must be in between 0 till 3. So the orders must be in between 0 till 3. 0, 1, 2, 3. We have 4 orders. In our curriculum, we have this range, but out of the curriculum, rarely there are order of 4 and 5, but it's much rare and it's not a lot. And the order of the reaction, guys, may be coefficient in some cases, or may not be coefficients. In some types of we will be solving the types, it will be equal to the coefficients. In some cases, we will find the order of the reaction. N plus M we call as the overall order of the reaction, guys. Overall order. N plus M, the range must be 0 till 3. In our curriculum, the range of this summation should be also in between 0 till 3, not exceed the 3. N and M use it to what? The overall order, N plus M, use it to determine the unit of specific rate constant, which we will use to determine the unit we'll be practicing. So the order of the reaction are those coefficients, are those powers which the concentration of reactant raised to, and must be individually in between 0 till 3, maybe the same as coefficient or not. The summation we call as the overall order, and the overall order must be in between 0 to 3. The overall order used to determine the unit of specific rate constant. K, or specific rate constant, we have some important notes on K. Let us talk about those notes, guys. The first one, if reaction orders, the powers are known, the value of K must be determined from experimental data. So we are not able to determine the value of K till we calculate the order of reactions. Second, the value of K is for a specific reaction. K has different value for other reactions, even at the same condition. Guys, for every individual reactions, even with the same conditions of temperature and pressure, we have different values of K's. So if we have millions of reactions, there will be million values of specific rate constant. The unit of K depends on the overall order. How? This is very important. I have represented here, guys. I will show you how to derive these units, but first of all, let me tell you, if the overall order is 0, the unit becomes ms minus 1 or L minus 1 mole S minus 1. If the overall order is 1, the unit is S minus 1. If the overall order is 2, the unit is M minus 1 S minus 1 or M mole minus 1 L 1 S minus 1. If the overall order is 3, there will be a unit of M minus 2 S minus 1 or mole minus 2 L2 S minus 1, guys. Let me show you how we derived those units. R is equal to K, the reactant concentration to the power of 0. The first one. That's the overall order of 0. Guys, if something to the power of 0, it will be 1. So in this case, R is equal to K. What's the unit of R? Is molarity per second. K, in this case, is equal to the molarity per second, or ms minus 1. Take to the numerator. So that's the ms minus 1. If you want to, instead of molarity, to write mole per liter, as you know that molarity is equal to mole per liter. So instead of molarity, write down mole per liter. ms minus 1 mole per liter S minus 1. Okay? take the liter to the numerator, you get what? Mol L minus 1 S minus 1. That's the second, which is mol L minus 1 S minus 1. Let me practice this for the when the overall order is 1. R is equal to K reactant to the power of 1, which is the overall order is 1. In this case, K is equal to what? R over reactant to the power of 1. R is molarity per second. Reactant concentration is molarity. To the power of 1, we will get molarity. So take this to the numerator. Molarity per second, multiply 1 over molarity. Molarity cancel out with the molarity. We will get 1 over S, or S minus 1. S minus 1. Let me do the same process for the when the unit, the overall order is 2, R is equal to K reactant concentration to the power of 2. Guys, this can be 2 reactants, A to the power of 1, B to the power of 1. So the overall order will be 2. We mean that, but I have combined in order to show you how the unit comes. K is equal to R over molarity square. So molarity per second, multiply 1 over molarity square. 1 molarity with 1 molarity cancel out, you'll get 1 over ms, or m minus 1 s minus 1. M minus 1 s minus 1. Or instead of molarity, just write down mole per liter. Mole per liter to the power of minus 1 s minus 1. This minus 1, you know math, when we open the bracket will be for mole and liter as well. So mol minus 1, L minus 1, S minus 1. Take the liter to the numerator, you'll get mol minus 1, L, S minus 1. Mol minus 1, L, S minus 1. And for the third one, guys, let me practice for you. R is equal to K concentration to the power of 3 cube of reactant. So K is equal to R over M cube, molarity per second, 1 over molarity cube, 1 cancel it, 1 over M square S, and you'll get M minus 2 S minus 1. M minus 2 S minus 1, or instead of molarity, just write down mole per liter minus 2 S minus 1. Mol minus 2 L minus 2 S minus 1, or finally mol minus 2 L 2 S minus 1. Mol minus 2 L 2 S minus 1. That's how we derive the units. This is very important because sometimes through the unit we'll be able to determine the order of the reactions as well. The fourth, guys, the value of K does not change for different concentrations of reactant or product, because rate also changes. K does not change with time. Guys, the value of K, here the K does not changes the rate of the reaction. The concentration. So the concentration, there are two quantities we may guess that changes the rate but does not rate. Concentration and time does not change, or they do not change the value of K. Okay, they do not change the value of K. The value of K for a specific reaction at a specific temperature, if we increase the temperature, increases the rate of the reaction and increases the K. We'll be talking about those two factors that increase the K, but the values of K independent on concentration of reactant and the time of the reaction. to say at the beginning, at the mid, or at the end of the reaction there will be new different case. So we do not have such case. You have to know that the unit of K, or the value of K, independent on temperature and independent on concentration and time. But the value of K depends on two other quantities, two other factors: temperature and catalyst. Changes K, guys, changes K, specific weight constant. So the specific weight constant somehow is the only constant that with the temperature some other value affects on, which is catalyst. The increase in temperature increases the rate of the reaction, increases the K as well. Catalyst also presence of catalyst increases the rate of the reaction, guys. Becomes larger when we have a catalyst in the process, and when we increase the increase the temperature, that increases the specific weight constant. So in summary, the time and concentration do not affect on or do not change the K value, but the temperature and catalyst changes and increases the value as we increase those two. Some notes we may have discussed about some of them. The unit of R is molarity per second or molarity per minute. M and N reactions order may or may not meet the coefficients of the reactants. Must be in between 0 till 3, those values. An order of 1. This is the meaning of the order, guys. When the order is 1, what's the meaning? Means the rate of the reaction is directly proportional to the concentration of reactant. R is equal to K reactant, order of 1 means they are directly proportional. If the order is 2, R is equal to K reactant concentration to the power of 2, means the rate is directly proportional to square of the reactant concentration. If the order is 3 cube, means the rate of the reaction is directly proportional to the reactant concentration cube. If the order is 0, what's the meaning of order 0? Means the K reactant concentration to the power of 0. Something to the power of 0, guys, is equal to 1. So in this case, the concentration of reactant does not affect on the rate of the reaction. In which case concentration does not affect on the rate of reaction? When the order is 0. And summation we call as the overall order. It should be in between 0 till 3, and we have got 3 types of questions: single step mechanism, reaction mechanism by using slow step, and experimental data. Let us solve for each of those types of questions, guys. The first one is a single step mechanism. What we have to know about this type of question, guys? For a single step mechanism, in the exam should say it's by one step mechanism. This reaction occurs in a single step mechanism or one step mechanism. Whenever it says is a single step mechanism, in this case the order equals the coefficients of reactant. So the order of the reactant equals to the coefficient in this case. Have a look on the above equation, guys. 2a plus b goes to form 2c, but we have to balance the equation first. Occurs in one step. When it says occur in one step, let us solve for a. Write the rate law, find overall order, respect to a, respect to b, unit of k. Guys, first of all, if it is first order, write that r, k, a to the power of 2, b to the power of 1. Why 2, why 1? Because the coefficient of a is 2, the coefficient of b is 1. That's how we simply equalize or find the order of the reaction through the coefficients. Second, the overall order is equal to what? Overall order, 2 plus 1, 3. Order respects to a is what? Is 2. Order with respect to B is what? 1. The unit of K. Unit of K depends on the overall order, which is 3. R is equal to K reactant to the power of 3. Okay? Cube. K is equal to R over molarity cube, molarity per second, multiply 1 over molarity cube, 1 molarity cancels, and then we'll get 1 over m square s, or m minus 2 s minus 1. This is the unit m minus 2 s minus 1, or in terms of mole per liter, we can say mole minus 2 s l 2 s minus 1. Guys, if we reverse the reaction, we have to change the rate law according to the reaction reverses. In the above equation, we have a to the square b to the power of 1. For this reaction, when we reverse the reaction, we write the rate law according to the reactant only. We do not include the product. So the reaction rate will be the concentration of C to the power of 2. Here we have got the sample problem. Let us solve a sample problem for this question in our book. Said a reaction involving X and Y was found occur by a one-step mechanism. So one-step mechanism, it's given in the reaction. It's what? X plus 2Y to form XY2. So simply, let us write the rate law. Rate is equal to what? K, X to the power of 1, Y to the power of 2. That's the rate of the reaction. Let us answer the following cases, guys. A, doubling the concentration of X. Let us double the concentration of X. When we double the concentration of X, Y is not mentioned, so let the Y as constant. Doubling this, 2 square doubles the rate. So the answer is what? We'll double the rate of the reaction. Doubling the concentration of Y, X is not mentioned, so let X as constant. Doubling this quadruples the rate. 2 square, it will be what? 4-fold the rate. Using 1/3 of the concentration of Y, 1 over 3 square will be 1/9. Reduces the rate, reduces to what? 1/9 of the original rate. So as we increase or decrease the concentrations, that increase and decrease the rate of the reaction directly. The second, guys, in a second type of questions is a reaction mechanism. When we have more than one step, there will be multiple steps. We have to follow the strategy that reaction mechanism is a step-by-step sequence of reaction by which the overall chemical change occurs. You know, we define the reaction mechanism is a step-by-step sequence of reactions which we add them to get the overall reaction. Therefore, in most reaction mechanisms, there are two types of steps, slow and fast. How to determine slow or fast? First, in the question, may write slow or fast. This is up here. Second, may write first step, step 1, step 2. Step 1 usually is slow and step 2 usually is fast. Third, if nothing is given, by intermediate, guys. This intermediate works for all types of questions. So intermediate appear in product of first step or slow step and reactant of fast. Intermediate must be in the product of the slow and reactant of the fast in order to know which one is slow, which one is fast. In some cases, we refer to the slowest rate as rate determining step. Why? Because we name it's another name for rate slow step. Why? Because the rate of the reaction depends on the slowest step, and the determining of the rate depends on that step. That's why we call as the rate determining step. And guys, the strategy, first of all, we have to determine the slow step, and as the slow step is known, it will be the same as the first type. The coefficient of the slow step becomes the order of the reactant. The coefficients of reactant of slow step are considered as order of each substance. Those affects the reaction rate law. Let us provide an example here, guys. In this example, it's written slow and fast, but let us process by the intermediate. Let us determine which species acts as intermediate. As you can see, NO3 appears in the product of here and NO3 in the reactant of there. So NO3 in this case is what is the intermediate, but NO2 is catalyst. NO3 is intermediate. So be careful about that, guys. The reaction rate, the rate law, depends on the fast step or the slow step. We just include the reactant of the slow step in the rate of the reaction. Why? Because that's a rate determining step. So simply, R is equal to what? K. What do we have? NO2. We can combine them to become 2NO2 and then NO2 squared. We do not include any of the other reactants of the steps and the net in the equation. Just the reactant of the slow step with what? With the power of their coefficients. Use coefficient number of reactant as the order in the slow step. Here the CO concentration does not affect on the rate. Why? Because it's not in the rate determining step. You may guess that YCO is not a part of the rate law because it's not in the rate determining step or the slow step. Let us solve a sample problem, guys. Set a proposed mechanism for this reaction, above reaction, follows by the two steps. The slow step, so it's given fast step. Write the rate law. So rate law is what? Equals what? The K NO2 to the power of 1, F2 to the power of 1. Why? Because the only reactant in the slow step are NO2 and F2. We just include the reactant of the slow step in the rate, and with the coefficients, with the order of the coefficient, these are the, or with the power of the coefficient, which are the orders. Another question, guys. Here we have got another question that if the step is not given, how to calculate the step? We have talked about this previously. This is the main equation, and this is the second step. How to, the second step is given here. How to find the first step, guys? Just flip the second step, which is NO2Cl, produce NO2 plus Cl, and add with the main, which is 2NO2 plus Cl2 to form 2NO2Cl. Let us add this together, we will get the first step, guys. NO2Cl with 2NO2Cl, what 1NO2Cl remain. NO2 with 2NO2, 1NO2 is the remainder. There is nothing else to be cancelled, so the step is NO2 plus Cl2 to form NO2Cl plus Cl. The rate depends on this because this is a slow step, or the fast step, equals K NO2 to the power of 1, Cl2 to the power of 1. That's how we can write the rate of the reaction. Find the unit of K. So the overall order is to find the unit of K, which is what? M minus 1, S minus 1. If slow or fast is not given, the slow step or the first step is the slow step, guys. Sample problem for the determining rate by using experiment data. The experimental data, we have to follow a strategy like this, guys. And if we have two types, one reactant and two reactants. Let us talk about whenever a set of experiments will be provided for the concentration and rate of the single reactant, follow the following step. a single reactant. There will be a set of experiment for a single reactant, which is in this sample problem is given set of experiment 1, 2, 3. First, choose 2 experiments randomly. 1, 2, 1, 3, 2, 3, 3, 1. And those experiments randomly choose 2 of them. Divide the higher value by the lower value. So for example, if we choose 1 and 2, the 2 is higher, so divide 2 by 1. I mean the experiment 2 by 1. Divide the same values of R. If we divide the values of the concentration, the second by first, we have to divide the value of R, the second by first as well. Equalize the result of the concentration and R. We equalize, there will be results of them. For example, if 0.030 divided by 0.015, there will be a number. We will equalize to the result of the R. And then equalize the base. We will equalize the power. And then order is equal to the power of the value of R. So we will be able to calculate the order. In this case, the order is not equal to the coefficient. We have to calculate orders through the experiments. Let me show you how to follow those procedures. Randomly, just 2 values, to take 2 of those values. For example, in this experiment, we have taken the experiment 2 and experiment 3 randomly. You can choose 2 and 3, 1 and 3. There is no problem. So, which one is higher, 1 and 2? 2 is higher than the 1, 0.030 to the power of n, this is the order we will be calculating, equals what to the divide by 0.015, this is equal to 2, this value is equal to 2 to the power of n, and 4.4 divided by 1.1 to the power minus 3, we will get 4. How to equalize the bases? Of course guys, mathematically 2 to the power of n equals 2 to the power of 2. So you have to change the R, results of the R, to be the same as the base of the n, as the order. So in this case, n is equal to what? 2. You know, mathematically, when the bases are equal, the coefficient, the powers will be equal. So n is equal to 2, and write the rate as equal to what? We have written that the K is equal to concentration of HI squared. And to find the value of K, guys, ask us to find the value of K, just take one of those experiments, for example, all the experiments, 1, 2, 3, okay, any of them, you'll be able to calculate the K. K is equal to what? R divided by concentration of HI squared. So 1.1 10 to the power minus 3 divided by 0.015 square, you'll get 4.9 m minus 1 s minus 1. Why? Because the order is 2. Always the higher value should be in the numerator, guys, and do not take coefficient number of reactant as the order. You know that in this case the reactant order is not the coefficient is not equal to the coefficient. Sometimes it's not given in the form of a table, may provide as this practice as this statement. So let us practice how to convert statement into what? Into a table, guys. For reaction 3A goes to C. So here we have got concentration of A, one reactant, with the rate of the reaction, molarity per second, and experimentus. At the beginning, write one molarity and 1 molarity per second. This is the first. Second, initially concentration of the initial concentration of A was 0.2 molar. So write, for example, here initial is given 0.2 molar. And the rate was 1 molar per second. So the first experiment is what? With having a concentration of 0.2 molar of A, we will get a rate of 1 molarity per second. When concentration of A was doubled, so second experiment, doubling the concentration of A, it becomes 0.4 molar, increases the rate to 4 molarity per second. 4 molarity per second. That's how we convert the statement into a table. So simply here you'll be able to solve for the order. Divide the 2 by 1 because the second is higher than the first. So 0.4 divided by 0.2 to the will equals to 2 to the power of n, and 4 for the r divided by 1 will get 4. So equalize these two. 2n equal to 2 square, n is equal to 2, and then r is equal to a to the power of 2. That's how we can write the rate law for if the given statement is if the statement is given. Sometimes the rate is given but tell you a condition. Guys, in this rate is given rkx cube, said by what factor does the rate increase if x is tripling? Just write the factor in the bracket and then you will see the effect. Tripling means 3 cube. 3 cube is equal to 27. So the second rate becomes 27 as the first rate. A second type of the experiment is two reactants. If two reactants is given, what to do? There is only a difference between this and the first type. In the first type, we choose randomly the experimenters, but here we cannot choose randomly the experimenters. For two types, for two reactants, follow the below strategy, guys. For example, if we have R, K, A to the power of N, B to the power of M. To find N, which is the order of A, choose two experiments, this must be the condition, which A changes but B held constant. To find M, which is the order of B, we have to choose two experiments which B changes but A held constant. So you have to choose those experimenters in order to find the order of any reactant. Choose those experimenters with that concentration of that reactant changes, but the other held constant. We will follow, and the other steps is the same as the previous type of questions. So guys, let us, the best way to understand, to practice a question, let us practice this question, guys. Say we have a reaction, AB goes to C. The set of experiments is given for A and B. 3 experimenters, we have 3 experimenters. Concentration is given with the R of the rate of the reaction. Suppose A to the power of N, M to the B to the power of M. Okay. Let me show you what to do to find N. To find N. Let us find N. To find N, we have to choose two experiments that A changes but B held constant. A in the first and the third changes but B held constant. So we have to choose experiment 3 and 1. Usually there will be one possible selection in this type of questions, guys. So the first and the third, A changes but B held constant. We are finding N. Which one is higher value than the other? Of course, the third is higher than. So divide 3 by 1. Experiment 3 by experiment 1. 3.1 or 3.6 divided by 1.2 is equal to what? Is equal to 3. 3 to the power of what? N. For the rate, divide 7.2 10 to the power minus 7 by 4 10 to the power minus, 8 10 to the power minus 8. This results a 9. Equalize these two, the same as the first type. 3 to the power of N equals 3 to the power of 2, because 3 square we will get 9. So n is equal to 2. That's how we calculated n. Let us calculate m. To find m, which two reactions, which two experiments can be used? M here is the order of B, so must be changed and A unchanged. The first and the second, A unchanged, but B changed. So use the first and second. First and second. Divide, which one is higher than the other? Of course, the first is higher than the second. 2.4 divided by 1.2 is equal to 2 to the power of m. And then 8 divided by 4, 8 to the power minus 8, 4 to the power minus 8 is equal to 2. The bases are equal. 2 to the power of m is equal to 2 to the power of 1. So m is equal to what? 1. Here we have calculated the m, which is equal to 1. And then simply write the rate law. Rate law is equal to k, a to the power of 2, b to the power of 1. Why? Because a is n to the power of n, b to the power of m. That's how we can choose, we can use this experimental data to solve for the rate of the reaction and rate law, to write the rate law. To find the value of k, the same, choose one of the other experiments. You'll be able to find the value of k. Randomly choose one experiment and put the values of all. You'll get the value of all of the reactants and the rate. You'll get the value of rate. The unit is mole minus 1 L2, mole minus 2 L2 S minus 1. That's the represents the third order. The next, here we have a statement: a hypothetical reaction involving L and M is found to double. So we have experiments, concentration of L, concentration of M, and R. Let us, the first experiment. Let us say L is 1, M is 1, R is 1. Molar per second. Okay, guys. Found to double when the concentration of L is doubled. Second experiment. The rate doubles, 2 molar per second, doubles when the concentration of L is doubled. So L doubled, 2 molarity. But how about M? M is not mentioned, so stay constant. If it's not mentioned, stay constant. The third experiment. And to increase fourfold when the concentration of M is doubled. The rate becomes fourfold, 4 molarity per second, when the concentration of M is doubled, 2 molarity, and L stay constant, 1 molarity. Stay constant as the first. So that's how we converted the statement into this table. Suppose the power of L is X, the power of M is Y, any values. In order to calculate X, we have to choose 2 experiments with the L is changes, but the M does not change. The first and the second, okay? The first and the second, M unchanged, but L is changed. So X, to find X, L to the power of X equals 2 to the power of X, 2 divided by 1, and 2 as well, the rate equals the rate, which is 2, and then X is equal to 1. The power of L is what? Is 1. And the power of M is, we have to choose 2 values or 2 experiments that the M changes but the L unchanged, the first and the third. 2 divided by 1, for m to the power of y equals to 2, and r is equal to 4 divided by 1 is 4. So 2 to the power of y, 2 to the power of y equals 2 to the power of 2. Y is equal to 2. And then write the weight law as what? R is equal to L1 m to the power of 2. Here should be 2. Or guys, simply, without performing this, in order to save time, set found to double the rate when L doublet. W rate, L doublet, so the same effect. That means the order of L is 1. But changes to fourfold when M doublet, that means the rate equals to the square of M. This is simply how to answer the question. At temperature below 200, this temperature is given. We have a reaction doubling the concentration of NO2 quadruples the rate of CO2. So quadruples the rate, that means NO2 is squared. Here is given. However, doubling the concentration of CO has no effect on the rate of the formation of CO2. That means CO is 0, or we can cancel it and do not write it. That's the end of the section, guys. Here we have got the test bank questions. I will be solving the standardized test prep to you, or let us solve some ministerial exam question, and then we'll be solving standardized test prep. Guys, the first one is said which one is odd. Probably the odd is one that exists the limit of the orders, guys. The C is the odd one because here 2 plus 2 is equal to 4. We do not have such overall order. The decomposition of nitrogen monoxide is this. The first step is this. How about the second step? So flip this, add with that, you'll get the second step. I will not be solving in order to not let the video to be much long. The decomposition, the same question. We have of nitrogen dioxide is this, occurs in 2 steps. The first step is this, which is the slow. How does the rate, if the initial concentration of NO2 is quadruples? How does the rate changes? Quadrupling this, you know that when it's the first step means the coefficients, let me write the rate law for you. The rate is equal to K, only NO2 to the power of 1. Why? Because its coefficient is what? Is 1. Okay, in this case, quadruples the rate, quadruple the concentration, quadruples the rate. Why? Because the coefficient or the order is 1. The initial concentration of A, so these are the types. What's the rate law for the reaction? We have solved the similar questions according to the following reaction. When concentration of NO2 is doubled, reaction rate increases 4 times. By doubling concentration of CO, reaction rate remains constant. If intermediate substance NO3, what's the reaction mechanism in 2 steps? What's the reaction mechanism in 2 steps? Guys, set this is the main equation. Okay? Set concentration of NO2 is doubled, reaction rate changes by 4-fold. But concentration of CO, reaction rate remains constant. R is equal to K NO2 squared. And CO 0, or we can say it's 1. So the reaction mechanism, the steps is given, is requirement. And said NO3 is intermediate. Guys, you have to choose a mechanism that only NO2 with the coefficient of 2 is in the reactant of the first step or the slow step, and the NO3 is in the product of that step. So, because NO3 or the intermediate is in the product of the slow reactant of the fast. Let us check the A. This is NO2, 2 is in the reactant, and NO3 is in the product, okay? And then NO3 is intermediate, this is fast. And second, if this is fast, slow, we'll get the same rate of the reaction. And we do not have what? We do not have the CO in the reaction. But when we add these two, we have to get the above. Let us add NO3 with NO3 cancelled out, NO2 with 2 NO2, 1 NO2 remains, and then let us rewrite the question, remainder. NO2 plus CO will produce NO plus CO2. We get the main equation and has the condition that the NO2 is in the reactant because the rate depends on NO2 only to the power of 2. And then NO3 is in the product of the first step. A is the correct answer and the others is incorrect. They are incorrect answers. Experiments is given. Find the rate law, which one is step, which one is slow. So you have to solve in a way that when we combine these two to get the above, guys. Have a look. Hydrogen cancelled with the hydrogen, okay? But here we have two hydrogens, so A is incorrect. Hydrogen cancelled with hydrogen again, but there we have two hydrogen, B is incorrect, okay? Here in the reactant, if we add reactants, we do not have hydrogen. The hydrogens are in the product, so here we have got two hydrogens. C is incorrect, so none of them is the correct answer. Activated complex is not intermediate. The slow step of mechanism of reaction is called the rate determining step. Rate constant for a reaction equals to 0.01 m minus 1 s minus 1. Doubling the concentration of reactant causes the rate increases by a factor of 1. Guys, this is the case I told you. Through the units will provide some questions. M minus 1, S minus 1 is the unit of which order? The reactant should be which order? Of course, we talked about this, guys. We said the unit is here must be used. R is equal to what? So just test the first, the 0, from 0, start from 0. K, reactant to the 0. So K is equal to what? M over S or M S minus 1. So this is not. Second, the second possibility. K, concentration square, concentration 1 is also S minus 1, is not. R, K, molarity square, okay? K is equal to R per molarity square or molarity per second, 1 over molarity square, 1 over ms or m minus 1 s minus 1. So m minus 1 s minus 1 is what? Is the order of 2. Order of 2. R is equal to what? K reactant to the power of 2. What's that? Doubling concentration, doubling this, quadruple the rate of the reaction. That's how we can answer the question. The same types of questions asking for the rate of the reaction. Another question, when doubling concentration of a given reactant quadruples the reaction rate, the coefficient or the concentration of reactant appears in the rate law with an order of what? Doubling this quadruples the other, well, the order of 2, exponent of 2, guys. The rate law relates what? Of course, reaction rate and concentration of reactant. There are several. The value of K in rate law is the same and under all conditions? No. Varies with concentration? No. Varies with time? No. Varies with temperature? Yes. That's how I told you. It does not depend on the time and concentration. It depends only on the temperature and catalyst. Here we have got the decomposition occurs in two steps. Sequence at elevated temperature. The first step is this. Which of the following is a possible second step mechanism? Just flip the first step and add with the main. You get the second step. A particular reaction found to have the following rate. Okay. How is the rate affected if the initial concentration of A is cut in half? Cut in half means just A 1 over 2A. So it will be what? The rate will be, reaction rate is half as well, because coefficient of this is 1. If it says cutting both in half, both, let me solve for that. So A cut in half, 1 over 2 square to the 1 is what? Cut in half, or let me just write another factor in order to be easier. To be doubling both. Doubling A will double the rate. Okay, double. And doubling B will quadruple the rate. So 2 square, it will be 4. 4 multiplied 2, you'll get 8. So the rate changes by 8 times, becomes faster 8 times as the R1. How is the rate affected if the initial concentration of B is triplet? B is triplet, 3 triplet. So it's 3 times. It changes to 3 square. It will be now 8. So reaction rate increases by factor of. Reaction it will be 9. Reaction rate increases by a factor of 9. Yes. By a factor of 3. No. By a factor of 2. No. Reaction rate has the same. No. So 3 cube, 3 square is equal to 9. These are all the possible questions, guys. I would prefer to you to solve the questions. I will be solving the standardized test prep. Here we have got the standardized test prep. The sequence of steps that occur in a reaction process is called the order, rate, law, overall reaction mechanism. Sequence of steps is the reaction mechanism, which is D. To be effective, a collision requires enough energy and a favorable orientation. See, this is a ministerial exam question. How does the energy of the activated complex compare with the energy of the reactants and products? Of course, it's higher than both. It's higher than both reactant and product. If a collision between molecules is very gentle, means not having enough energy, molecules likely to be oriented favorably. It's not about orientation. Less likely to be oriented, likely to react, likely to rebound without reacting. D is the correct answer. And then a species that changes the rate of reaction but is neither consumed nor changed is what? Is a catalyst, guys. A catalyst is that species. Question number 6. A rate law related to what? This was the ministerial exam question. Related the reaction rate and concentration. B is the correct answer. In a graph of how energy changes with reaction process, the activated complex appear on the peak of the curve, which is the crest. A certain reaction is zero order in reactant A and second order in reactant B. What happens to the reaction rate when the concentration of both reactants are doubled? So let me write the rate law for this, guys. R is equal to K. A is zero order in reactant A, and reactant B is second order. So this has no effect. Doubling the both concentration with quadruples what? The rate. Where is the quadruples? The rate. So the rate remain constant? No. The reaction increased by a factor of 2? No. By a factor of 4? C is the correct answer. That's how we can use the slowest step in a mechanism is called the rate determining step, which is A is the correct answer. Thank you for the attention. That's the